Coffee break. Everyone was really good in coming back. We didn't even have to ring the bell. So our next speaker is Wei Zhu from the University of Alabama, and Wei Zhu will speak about Euler's elastica-based segmentation models and fast algorithms.
Okay, first I would like to thank you, organizer, for giving me this great chance to give a talk here. And today, so I would like to talk about our previous work about Euler elastic-based segmentation model. It basically consists of two parts, and this is these two works basically joined with Igir, Tony Chen, and Xuechen Tai in the past few years. Okay, so first let me quickly talk about the outline for this talk. So I think the image segmentation problem is too old, but I still would like to mention quickly so that you know what kind of topic I'm going to discuss. Okay, and also I would like to review the previous works, and then one by one we would like to introduce the work about using Euler elastic for the segmentation stuff. And then we will also discuss a faster algorithm, basically use the augmented Lagrangian method. And then we will present the result. Following that, we will discuss a summary and future works. Okay, so the thing is image segmentation basically try to capture object and try to segment the image domain into several parts, and each part represent a kind of object. So here I would like to choose some kind of natural picture, okay, some kind of tiger. So if we apply this kind of intensity-based segmentation model, so with the length as the regularization for active contour, so it is very probably that is we cannot find this kind of tail, because this tail we have this kind of at least first it's broken. So not because of the tiger itself, but because of the intensity, black and white. So that is how can we capture this kind of tail as complete as possible. If we are using those standard ones, probably not that good. So that's why based on this kind of stuff we would like to discuss Euler elastic. But before we talk about our model, so we would like to review a little bit. And all these kind of models kind of old, but still very useful. The first one is most famous snake model. That is, this kind of C represents the curve, active contour, and this gradient F. Okay, so basically the first two terms just characterize how this kind of curve should be. So that is regularity stuff. And this term basically that is, so on the boundary of object, so basically the gradient F. So here this F is the given image. So if on the boundary, so basically this kind of gradient F should be very large. That is when this kind of C, that is the active contour, locates on this kind of boundary, so this term should be very big. So that's why, so in the variation method point of view, that is, if we minimize this one, we hope this kind of stuff is the largest, so that we can find the boundary of object. And after a few years, so that is, this is also another very famous model, the geodesic active contour model. So that is here. So again, very similar as the previous one, but they put everything inside this G function. This G function is called age function, and it is equal to, okay, when x equal to 0, so equal to 1, and after that, so keep going. That is strictly decreasing. And again, if we minimize this one, so that is, we kind of like that this kind of gradient F should be as big as possible, so that once this kind of curve touches the boundary of object, this one is kind of minimized. Okay. Anyway, this is the idea. And in fact, more than that, so that is in 1989. So one of the most famous model in variational using variation method in mathematical imaging is given by Mumford and Shaw. So this model, that is, besides the boundary, also consists the denoised stuff. That is here, this U is a clean one, and K is the boundary. So that is, so this term basically we always consider called as a fitting term. And this one makes the clean image as smooth as possible. And this one is the length of the boundary. Okay, this we can say a Hausdorff measure for, okay, for the length. Okay, so that is by minimizing this one, so we hope the clean image should be very close to the given f, and also so this kind of length cannot be too much, so we don't allow the too much this kind of boundary, and based on this kind of boundary, cut this kind of origin into lots of small pieces. That is here we can see that is the gradient square. If we take the Euler Lagrangian equation, this is Laplace u. That is try to smooth the stuff. That is in each small piece we want to have the clean image as smooth as possible. So this is a given. This is a result from I guess from Numerical based paper. Okay, I copied it from there. So that is here you can see some picture. This is original picture, and you can see this boundary, and this is a given u. Okay, and in fact, the Mumford-Schultz model has been widely used during the last 3 decades. And then here, so mainly we would like to talk about the Chern-Weisses model. So Chern-Weisses model could be regarded as a special case of a Mumford-Schultz model, because for this model, for the previous u function can be treated as a binary, that is either 0 or 1. So but the good new stuff is so different from the previous Mumford-Schultz model. It's kind of very difficult to characterize the boundary k. So this k, okay, this boundary can be easily captured using level-set method. I think that is a very nice feature for this one. Okay, so here these first 2 terms basically still the fitting term, and this one is the length term. So that is basically characterize the length of this kind of boundary. So basically, our model mainly focuses on how to revise this kind of term, so which we will be discussing. Okay, so the thing is, first we would like to talk about this is a long time work, that is almost 4 years ago, and this is basically okay. So Chern-Weisses model will use this kind of length as the regularization for active contour. So the thing is, we would like to change that. So we would like to change using what? Use basically Euler elastica. So Euler elastica, so by definition, so typically like this kind of stuff, that is gamma is some curve, okay, and this kappa is a curvature, and dA is arc length, and A plus B kappa square, so basically Euler elastica. So we try to minimize, okay, we try to minimize this term. This is minimizer, we call it Euler elastica. Okay, and if this one is not a closed curve, so basically that is 2 endpoints should be given besides the position and also its tangential stuff, right? Okay, so then we can rewrite this kind of Euler elastica using level-set method. So that is here phi is level-set function, and this is basically just using level-set setting to rewrite this kind of Euler elastica, which we will using this one for our model. Okay, so almost 4 years ago, so we developed this kind of model that is basically using Euler elastica as the regularization for that is replace the previous Chern-Weisses model. So the first term, the fitting term, still exactly the same. So that is, you can see h phi is a positive one, or this is 0, or something reverse. Okay, so by doing this kind of very simple substitution, we find that it does give us a lot of new features. So most important one is completing those kind of broken parts. So that is why at the very beginning I showed the picture of the tail of the tiger. So that is, it can connecting this kind of broken parts automatically, because that is give us a small curvature part. And also second interesting feature is can capture objects of relative larger size by omitting those relative small size. And the third one is more suitable for capturing elongated structure. Okay, so it probably has kind of application in blood vessels for this kind of segmentation. So in the following, so we would like to quickly talk about why we do have this kind of interesting features. Okay, so I think the first one, most important thing is capture objects of larger size while also omitting those small size. So this is basically depends based on what? Based on the Euler elastica. So why is that? So we can see that for any closed or piecewise closed and piecewise smooth curve C. Okay, so we here k means the curvature. Okay, so if we have the absolute value, then do integration. So always it should be greater or equal than 2 pi. Because what? Because the curvature that is basically in differential geometry, we know that is d theta over ds. So that is theta. If you have one loop, so always convex, that is exactly the smallest, that is 2 pi. If you do this kind of oscillation, so that is will give us a larger one. Okay, so that is if we know this kind of inequality, so we can find that we use a Holder inequality. That is we can change to be okay. So kappa square. Okay, so kappa square. Then we find this one just the length of the curve. Okay, and this is just kappa square, which we just one of the important part for the Euler elastic term. So that is by doing this kind of simple calculation, we find kappa square. Okay, integral along some closed curve. So it should be greater or equal than 4 pi squared divided by its length. So that means what? That is means this kind of term. Okay, so kind of reciprocally depend on this kind of length. So if this length is very small, it will give us a very large Euler elastic term. So that's why. So for example, here I just draw these 2 circles. We find that is if we choose the parameter b, that is before the kappa square term. Okay, so we can find that is only can capture this kind of one, the bigger one. This smaller one will be treated as a part of the boundary background. So I think this is the most important reason. Okay, so then why connecting this one? I think this is basically from our common sense. We know that because the thing is, if we, instead of connecting this kind of stuff, so those kind of corners, okay, we should have a very large value for the Euler elastic. But if we connect this kind of stuff, that is almost theoretically the curvature is 0 along this one. But even though we could sacrifice for this kind of fitting term, but in case the b term is kind of larger, so the fitting term means nothing. So compared to the curvature part, okay. And based on these 2 features, the above 2 features, we can find that is more suitable to capture this kind of elongated structure than the previous Champ-Bases. Because what? Because the thing is for which I will show the picture afterwards. So the thing is could capture, so Champ-Base, so if the length, the parameter of the length is not that big enough, they could allow lots of small dots. But however, by using Euler elastic, these kind of small dots cannot be allowed. So that's why prohibited. So that's why we could have this kind of elongated structure stuff. Okay, so this is basically we try to explain why this kind of a new change could introduce such features. So details can be found in our previous paper. Okay. Okay. So then, so the second thing is so when we talk about this kind of Euler elastic, so how can we minimize that? So to minimize that, so basically that we think that is too complicated because this is the second order stuff and also nonlinear, and also we have non-differential term. So because this kind of denominator, so that is if we try to derive the Euler Lagrangian equation, that should be fourth order. So but recently, okay, so quite a lot of research work have a focus on this kind of how to develop this kind of fast method or reliable method to handle this kind of fourth order stuff. So also including those fourth order PD stuff. Okay, so here we only list one choice which we would like to use here. That is basically we would like to use augmented Lagrangian method to revise or rewrite this kind of stuff as an optimization problem, and also by introduce lots of dual variable or dual variables. To change that, to make it low order, and each of the low order can be solved easily or quickly. Okay, so that is to discuss the augmented Lagrangian method. So I would like to use a few slides to discuss how this kind of technique can be used in the previous works. So basically, so what I follow is always given by this Xue Chengtai's previous work on the this is ROF model, and also this is for Euler elastic-based image denoising model. Okay, we call it Ambrosio and Massimo and Morris Euler elastic model. Okay, so that is the first. Let's focus on the Rudin-Auschel-Fartumis model. So it's non-differentiable and non-linear, right? Okay, and I think for this one, most important stuff is always if we are going to use Euler Lagrangian equation to solve that, that is basically we have to use because this is non-differentiable, we have to use a revised version to approximate that. That means not that accurate. Okay, well, that is accuracy cannot be guaranteed. And for this one, since this is Euler elastica, more complicated, so that is whatever. So if Euler Lagrangian equation could be much complicated. Okay, so anyway, so we basically follow these two papers given by Shushinte and his collaborators. So the main idea of augmented Lagrangian is basically, okay, convert the original optimization problem to be some constraint optimization problem. And to find the minimizer for this kind of optimization problem, so we basically we would like to try to find the optimization for its saddle point. So, but for saddle point, it depends on the problem. For this one, so I think optimization can give us a very solid theory. But for this a little bit complicated one, so lots of theoretical stuff still at large. Okay. So anyway, so the key idea for the augmented Lagrangian is whether or not those sub-problems can be solved efficiently. So if it's still very complicated, so why not use that? So that is okay. So then first, I would like to use this slide to discuss so how to use augmented Lagrangian to minimize the ROF model. So that is the idea is first try to introduce a p variable to replace this gradient u. So that is here we would like to minimize u and p, and for this one and subject to this kind of constraint. And to minimize this kind of constraint problem, so basically we try to find a saddle point for this augmented Lagrangian. And to find the saddle point of this augmented Lagrangian, so basically we try to solve each of the corresponding sub-problem, that is by fixing p or fixing u. So we do that alternately and repeatedly until so convergence can be achieved. So that is, if we look at the p problem, so this p problem, we write this kind of stuff. If we do some standard manipulation, we can find that it has number p absolute value plus a quadratic form about p. So that is this is from the optimization theory. That is, it has some closed form solution. They call the shrinkage solution. Okay, and for this u, if we this u, that is, if we try to find that, because we cannot write down its minimizer using some closed form, but so if we try to find the Euler Lagrangian equation, that is just linear. Okay, just linear. So we can solve using FFT. So that is in this way. So each of them, so this closed form solution, and this can be solved using FFT. So that is in this way. So it's a saddle point, and also the original minimizer can be quickly found. Okay, and then let's move to the how to use augmented Lagrangian. So to minimize this kind of denoising model using Euler elastica as the regularizer. So this again from Shushintai's 2011 paper. So maybe this stage call it GHC algorithm. Okay. So that is the idea is like this one. So first introduce as before, introduce p, okay, equal to gradient u, and also because this curvature depends on this kind of the normalized gradient u. That is also introduce this n to equal to p divided by its length. That is normalized p. And so if we directly consider this kind of problem and also derive this kind of augmented Lagrangian functional, so since we have this kind of constraint, that is n equal to p divided by length of p, so this is not that easy to handle, because if we do the expansion, that is big, we should have at least we should have one term, that is p length p time p dot n. So that is, this is a non-differentiable and non-linear, this kind of stuff. That is very difficult to handle. So that's why in Shushintai's paper, so that is to relax this kind of constraint, they introduce another variable that is m, called m. So they say that is a letter n equal to m, and m equal to p divided by the length of p. So that is, if we omit this n, that is the original one, but introduce this kind of stuff, that is because the previous n involves the previous calculation, but here this m could be independently. So that's why here says that is, and also besides this one, so m equal to this kind of normalization for the p, that is, can be equivalent to be this length of p equal to m dot this p, but require this m should be, the length should be less or equal than 1. So that is in this way. So that is a previous constraint can be changed to be this kind of stuff. That is this one. So introduce one more variable, and but makes it easier. Okay, so that is again. So this is the augmented Lagrangian method. functional. So here, I think the most important stuff is this term, okay? Because whatever this kind of term always a square, but this one does not have. Because what? Because the length p minus p dot with m should be always non-negative. So that's why a square is unnecessary. Okay. So then, the benefit is this kind of stuff. That is, once we solve the minimizer sub-problem of p, that is, again, since there's no square term, so we can still do the stuff that is length of p and some p squares, this kind of terms. Also has a closed form solution for this p. And for this m, also closed form solution. So in this way, all these sub-problems either have closed form solution or can be solved using FFT because they involve linear elliptic equation with constant coefficients. That is, can be solved using FFT. Okay, so that is basically the augmented Lagrangian for this kind of stuff. Okay, then we would like to use the idea, in fact, almost the same idea for our problem. So Euler Lagrangian, Euler elastic L2 model. So L2 means because we have a cover square, so that's why we call L2. Okay, so how to do this one? So the thing is, here we do something changed, right? So because the thing is here, basically for a lot of numerical stuff, that is, we will not use this kind of heaviside function directly. We would like to use its regularization term. Okay, if we use its regularization term, we find if we introduce u equal to this kind of heaviside function, okay, then they should be the same. Okay, in this way, we can rewrite this kind of stuff. That is, use u to replace the previous h phi, and then replace this one and this term. So that is, everything just can be written in terms of u. And but here we should subject require that u should be 0 and 1. But this one we can relax to be 0 and 1. So make it becomes a kind of like a convex stuff, convex problem. Okay, so then, based on the idea of augmented Lagrangian for the previous Euler elastic stuff, then we can also derive this kind of rewrite this kind of optimization problem, and also develop this kind of augmented functional. So the thing is, here we introduce v. The reason is because we require u must be inside 0 and 1. So that's why here we put this kind of delta function that is either 0. That is when this kind of v is inside 0 and 1. So that is 0. Otherwise, it should be infinity. So that is we require this v should be inside 0 and 1. So in this way, we can have all the stuff that is all these sub-problems. So that is first about v and p and m. So each has a closed form solution. And for u and n, so give us this kind of two linear equation. For u. And this one, so coefficient is not constant. It's not constant term, but basically we would like to use a fixed point method. Okay, and still using FFT to solve the second equation. So in this way, Euler elastic based CV model can be solved quickly. Okay, so here I would like to show some numerical example. So first the thing is, let's see the UCLA, this kind of picture. So we can see this kind of the broken parts. Okay, so but for our home beam, it's very easily to recognize UCLA. And here I would like to do the comparison between the proposed model and the Chanvesis model. So Chanvesis model, so here we find that is this kind of stuff cannot be connected. Okay, cannot be connected. And for this one, so you can see this connected very well. And if you zoom in this kind of stuff, you will find that this kind of part, the gap is, if we are very clear about this kind of TV stuff, so that is this kind of gap is a little bit longer than this kind of the width of the u, the length term. Okay, that is basically theoretically for Chanvesis model cannot connect this kind of stuff because the width is bigger than the gap. Switch. The gap is bigger than the width. Okay, and then so let's focus on this kind of type of picture. So we find that by using the Euler elastic as the regularization term, we can find this kind of tail can be, I cannot say completely captured, but lots of part captured. But however, for this one, so Chanvesis model, so we can see lots of broken parts. Another interesting thing is, as we previously discussed, that is small parts, small dots, this kind of stuff, or small parts, so cannot be kept by this kind of Euler elastic-based model. And however, for Chanvesi, you can see this kind of dots, right? So this kind of dots. Okay, so that is basically, as we discussed previously, so the curvature term should be greater or equal than 4 pi square divided by its length, its perimeter. So that this perimeter too small, so cannot show up here. So that is why. Okay. And this one, so that is also we talk about how to ignore this kind of small objects. So that is here we have 2 eagles, the bigger and the smaller one. So if we choose the B kind of very, very small, okay, that is a 0.1, so we can find that it can capture both of them. That is a bigger and smaller one. And however, if we make the curvature term so that is stronger, this one will be omitted. So the smaller one omitted. So that's why we say this is.
Does it also capture the tail? Or
what's that?
The white tail.
Both the tail, I think, are not captured. That's treated as the background. Yeah, but we basically focus on this small bird, small eagle. That is that not captured by using b equal to 2. Yeah. And then we talk about this Wei Zhu stuff. So the thing is, this one again given by Chanvesi's model, and this is given by Euler elastic model. So the thing is, we can find. I think the picture probably not that clear, but the thing is, in the real one, so this lots of kind of not connected, well connected, at least not well defined connected. And for this Euler elastic based model, so connected well, and for this one, so you can see not connected, and see small dots. And here also we have lots of dots, but here no dots. So that is elongated structure can be captured well. Okay, so then I think the first model is done. Then we would like to move to the second model. Second model, so basically the story is like this one. So previously when we use Euler elastic as a regularization, I think it basically because what? Because previous Shuchen-Tai, the augmented Lagrangian method with successful Euler elastic denoising model. So that's why we discussed using that one. But for this one, so almost 2 or 3 years ago, so once Shuchen-Tai discussed with me that is how about so try to capture convex shape. Okay, that is. But previously we didn't think about this one. So that is from the formula. It seems like automatically we think about this, but the truth is not. So we think about it for a while, and we find finally we do have some geometric feature for using this kind of variant of Euler elastic, because previous Euler elastic always we have a kappa square, and for this one no, the thing is we use absolute value of kappa. So this is basically because this kind of important theorem from differential geometry, that is if gamma is a piecewise smooth closed curve, okay, in R2, and then we must have this kind of inequality. But in fact, previously I mentioned in one of our slides I use this kind of inequality. And the equality, holds when this gamma is convex. So that is once this one convex, as we just discussed, the thing is kappa is d theta over ds. So that is if we do this one, so theta will always keep going, so keep increasing. That is basically just one loop. That is why we have 2 pi. So we try to use this kind of stuff. So that's why here we just use L1 for this elastic. Okay, so the thing is, but here we would encounter different issue. Why that? Because once we introduce this kind of stuff, previously is kappa square. Now we have a kappa just absolute value. So if we are going to follow the same idea as before, so we should have more and more, at least one more sample problem. So that is, then we should have 5 or 6 penalty parameter to choose. That make our numerical stuff much more harder. So that's why here we try to do some change. Okay, so that is here. First, I would talk about if we just directly follow what we just discussed, the method for Euler elastic stuff. That is, we do the same thing as before, and then we do have this kind of stuff. So if you look at this one, you will find that is we should have one more term. That is q. Q equal to previous we don't have this kind of term. Okay, now we do have this q equal to divergence. That is basically the curvature stuff. Okay, so that is if we follow the idea as before, then we would like to derive this kind of augmented Lagrangian functional. So we can find here R1 to R5. So previous, I think we have only have four. Four. So that is here we have 5 penalty parameter to be choosing, and also for sub problem we have V, U, Q, P, and M. So that is 6. So sub problem need to be solved. Okay, C1, C2 here we don't care at this moment. Okay, so that is basically the issue is like this one. So okay, so besides this kind of numbers, okay, that is sub problems and penalty parameters to be solved, to be determined, and the limit is like this one. So if we try to represent the curvature faithfully, okay, so that is in some sense that is we should have all this kind of parameter bigger. So that is so that we do have exactly this kind of relation. That is, I cannot say it's strictly bigger. That is relatively bigger. However, if we do that, so that will of course will affect this kind of fitting term. So, but the fitting term, so for the segmentation block, I think is almost the most important stuff. So this is different from denoising problem. Denoising problem, the denoised one always close to the given image f. But for this segmentation, the curve could be whatever place. That is no those kind of strict constraint stuff. So that's why. So we try to think about using new augmented Lagrangian method. That is here. That's okay. So what is our goal? So because we kind of sick of using too many penalty parameters, so that's why our goal is we try to use a few one. Okay. So few Lagrangian multipliers, and also so we try to represent the curvature more reliably or effectively. Okay. So to do that, so here instead of as previous, that is a u equal to h phi to represent everything. So but here we will stick to this kind of phi because we don't want to introduce one more parameter. Okay, so that is as we previously said, we try to use approximate this kind of use a very small epsilon. Okay, that is kind of like this kind of function. Okay, then in this way we can rewrite the model in this kind of way. So looks complicated, but not that complicated than the previous one. So, yeah, okay. So then, so let's try to consider this kind of constraint problem subject to. Now we do have a few, much few. Okay, but the thing is, since our goal is try to, as we just said, that we kind of sick of using too many penalty parameters. That is, we try to, at whatever cost, to reduce the number of parameters. So that's why at this moment we try to introduce this kind of constraint. That is. P, okay, the length of P times n equal to P. So previous in Schwarzenegger's work, they try to avoid that by introducing another variable, which is M, to relax this kind of constraint. But here we just face directly, okay, this kind of constraint. So in this way, we only have 3 parameters and 4 sub-problems. That is decrease quite a lot. Okay, so good news is so no restriction for the previous level set function, and also so we only have 3 Lagrangian multipliers. But the thing is, how can we find? So how can we handle this P, corresponding P problem? Because as we previously discussed, if we do the expansion for this one, we should have length P time P then dot this kind of n. So that is more complicated, nonlinear, and yes, and more complicated, non-differentiable. Okay, so if we do this one, so except this kind of P, all these 3 can be solved either a closed form solution or can be solved using FFT stuff. Okay, but how to handle this one? So in this one, basically I discuss how to solve the first sub-problem, and this is for second 2. Okay, so third one, second one, and third one. So in fact, the most important thing is how to solve this minimizer. Okay, this sub-problem. So to solve this sub-problem, so we would like to do what we try to express in this way. So reformulate in this way. That is, we treat all the other ones as constant, and this P, okay, and this also P. That is finally because this kind of sub-problem will not involve the derivative. So that's why. So we can, in some sense, that is a point-wise solved, not just solve this kind of integration stuff. That is basically we need just consider this kind of calculus function, right? So that is scalar function. So how to minimize this one? So the first term and the second term relative, if we don't have the third term, that is basically, that is we have a closed form solution. However, we have here, that is x and the length of x, as we discussed previously, that's not that easy to handle. So to do this one, so we propose some kind of theorem. We discuss several cases. That is, once mu is the previous one, okay, that is, if this mu is greater or equal than 2 times, okay, this kind of the nu, okay, the length, okay, then we must have this kind of stuff. That is, the problem for this calculus problem we can solve. We cannot say accurately, but very close, because in some part we do have exact solution, and some, in case we cannot have, we can use Newton's method just directly solve this kind of equation. Okay, so in this way, so we can solve this subproblem because of what? Because the previous one mu equal to this one and nu equal to this. Of course, mu is greater than 2 times this can do. That is, the assumption of the previous theorem is satisfied automatically. So that's no problem. And then, so by solving this kind of subproblem based on the optimization theory, that is, we also need to change, update those dual variable or Lagrangian multipliers. Okay, and according. And for the numerical issue, that is, once we do the numerical stuff, so we try to track. So whether or not we do get some kind of approximation to the saddle point or some point which could give us the information of the minimizer. So we basically try to check this kind of residues and relative errors. Okay, so in the following, so we would like to discuss the numerical experiment. Okay, so the first one, so basically which we call that the data-driven property. So in this figure, this is synthetic image. So, and we find that if we let b very small, so almost each object will be captured. Okay, and once we have this going to be a little bit bigger, so we find that this one will be missing. And if b even bigger, so that is this small ones also missing. Okay, and if we look at this Pac-Man, so we find that is here the bigger mouse. Okay, and this one the mouse almost closed, right? Okay, and this kind of convex one all captured. So in this kind of experiment, basically, I would like to show that so this data-driven, that is b if bigger enough, that is the small ones will be skipped, so as treated as the background. Okay, and then the next one, I still use this kind of image to show the stuff is because this kind of image, this is synthetic image. So purposely, I made the first row, these 3 objects, the area the same, exactly the same. But still, from the previous example I copied here, so the thing is, if I make b very small, that is all these 3 objects could be captured. However, if I make it a little bit bigger, so we find that is this one will be omitted. So the reason is what? Because this object is non-convex. So if you capture that, the Euler elastic term should be very big. So that's why sacrifice the fitting term. And but however, for this kind of convex one, so that is still preserved. So that's why we call this one shape-driven property. And then we move to for real example. So this real example, so we have a boy, okay, with a big black hat, okay. So if we are going to use a standard intensity dependent segmentation model, so of course we can find that it's like this kind of stuff, or at least this kind of part. That is, this kind of his shadow should be treated as the boundary, no, treated as the background. So that's why. So in our model, so if we choose b relatively small, so that is we can see this kind of there's a dent here, and if we make b bigger, so that is moving out. If b kind of big enough, so that is almost convex, almost convex. Okay, so that is as we make this b big enough, so that's constraint. So L1 or Euler elastic, so we'll take this kind of part. Okay, that is this kind of stuff. Is, the Euler elastic term is too big, so that's why for this one, so it becomes convex. And this one is for the previous one, that is convex from outside, inside to outside. For this one, this is a mushroom, so we can see there's a cap and a stem. Okay, if we would like to use a standard stuff, say if I make this b very very tiny, say close to 0, that is basically we can capture all the mushroom. So that is besides its cap and also its stem, and also all these kind of parts. Okay. However, if we make b bigger, okay, so that is a shrink to inside, so that if we have b equal to even bigger, almost a convex contour. Okay, convex contour. Yeah. So these plots basically try to show that So this kind of repeated process that is try to converge, okay, to somewhere. Yeah, I think this almost finished my talk. So that is in this talk. So basically, we discuss two Euler elastic-based model. Okay, and each of them introduces some new features, especially data-driven and shape-driven properties. And also in these two work, so we introduce the augmented Lagrangian method to minimize the proposed functional. And future work quite a lot. So in fact, only I discuss here two. That is, we still, because at this moment we still think that curvature stuff, that is how to effectively capture curvature, is not, it's still a big issue. So that's why I say more reliable and efficient method still at large. Okay, and the convergence analysis. So because involve curvature, so I think very few stuff. Study has been done. So that's why this is our dream stuff. That is, in the near future, we try to do that. Okay, I think that's it.
Thank you very much.
Thank you.
What kind of curvature measure should be used in three-dimensional case when you, for example, like to...
Oh, you mean 3 dimensions, right? Yeah. So here, basically, we talk about 2 dimensions. So in case you talk about 3 dimensions, I think, to my understanding, I prefer Gaussian curvature. Yes.
Why?
Because we do have a very beautiful formula for the, what is that, Gaussian bound later, this kind of theorem. Yeah. Oh, it's a nightmare. So that's why I say, so we try to find an even more reliable and effective method. Yeah. Yes?
But I thought that when you do augmented Lagrangian, you kind of let this parameter slowly increase until you find a solution that satisfies the constraints. You're not doing that?
I didn't.
Well, when you read the augmented Lagrangian from Nosether and Wright, for example, which is the only thing I did, they suggest that the penalty, what you call R1 to R5 or 6, you just make them increase progressively until you find a solution that satisfies the constraints. That doesn't work in your case?
I think that is a good idea. In fact, in my other works, I did use that kind of strategy. But the first thing is, in case, but still that one, we need to know that is how to choose them initially. And since this kind of parameters always this kind of quantity connected with each other, so we still need to find what's the relation between R1, R2, and R3. If someone too big, that is, you make that constraint tight, which is good, but you cannot make other one. So that is this kind of still, I think, a big problem. Yeah.
You mentioned the parameters.
Yes.
Which one do you increase first?
Well, altogether.
Altogether, so which one is so big? Which one is bigger? Which one is
you have
small?
You have to find the good relative weight, as you were saying.
Yeah. So that is make our tough problem become another tough problem. That is how to choose those parameters. Yeah.
Apart from the Lagrange multipliers, also your coefficients A and B.
Yes.
To be handpicked per image to get the result.
In fact, for that two parameters, I'm not worried about that because that is basically the model's parameter. So that is, if we try to have, for example, elongated structure, so that is A term could be very tiny because we don't penalize those elongated stuff because it's big length. And B, so we can choose as what we want, right? If we should be bigger.
Yes, but still, it should stay the same. Hopefully, these parameters for a good number of images you're interested in.
Yeah, so that is still depends on the image, those kind of stuff. But basically, so for our problem, so the thing is, I think A, B, we can originally we choose that. Whatever result, because the thing is, we try to check those kind of residue stuff. So once A, B, choose it. If we can find this kind of relative error, both go to all go to somewhere, go to 0, close to 0. That basically we think that is a solution corresponding to this AB. If this AB is this result is not what we want, probably we should adjust those AB.
So it's sounds like there's human interaction necessary.
Yeah, probably we have to get involved. So what kind of result do you want? So
I guess to have it as automatic as possible.
I think probably these days can use machine learning so to choose this kind of stuff. Yeah.
Yuri.
Just want to comment on the distinction between minimizing curvature and convexity of a shape. Because convexity is more like of a global property, so unless in your results, you had like a binary segmentation, right, in your results. So
Yes.
convex would be one segment for the whole thing. You cannot just have disconnected convex parts.
Oh, you mean so?
Yes.
Very nice suggestion. So in fact, I didn't try this kind of stuff, but in my point that is, we could have multiple connected, but each of them. Oh, wait a second. Do I have the result? Is that what you said?
Well, for example, here, if you enforce convexity, it would be in the end one segment. Right now, your segmentation is not convex, right?
Yeah, this is not enough for convex. So that is theoretically okay. If we increase this one, okay, that we hope that I'm pretty sure that is this Pac-Man, the mouth should be completely closed. Yeah.
I mean, like, this is binary segmentation, right?
Yes, this is binary.
Like, enforcing convexity on your segmentation is... I'm just saying that there should be more careful distinction made between minimizing curvature and enforcing convexity. It's like somewhat different properties.
Yeah, I agree.
And that's
Yes.
all I'm...
Yeah, I agree with that.
Because
Yeah.
you're trying to make this connection, but I think that's...
I think we still should have we still have lots of work to be done, just follow this one. But I think at this moment the numerical stuff of doing this kind of curvature one is a bigger big burden for us. So that is kind of prevent us from moving forward. I think your question is very nice, and yeah, probably in the near future we can pursue that.
How critical is the initialization?
How
Because
was it?
as far as that you do curve evolution, so it means if you initialize very poorly, you might just not reach any good solution.
Yeah, very nice. So the thing is, in fact, for the result I should here, so I didn't purposely choose the initialization. I just draw a big circle, just almost cover. I can't say cover. Just I like this kind of stuff. So for example, this image, I just do this big one. I didn't choose something else. Always for each of them, I do this kind of circle, bigger circle, just inside the region of inside this kind of region. I didn't choose other initialization for the phi function. Maybe I should choose.
But you also optimize over C1 and C2.
Yes.
So which
C1, C2 basically that is the average inside and outside.
So it could mean that with your way to initialize that you have basically these averages are very, very close. And
Yeah, I agree with you because whatever stuff, this kind of elastic based model is non-convex. It's non-convex. So that is, if I choose, say, this kind of level set function that is close to this one, probably just find this one because it could give us a local minimizer. So without finding other ones. But for this kind of stuff, as I said, always I put a big one. Yeah, and let it go.
Usually people do egg-tray initialization, so a lot of
Oh, you mean small circles, right?
and then you catch also if you have a hole in
Yeah. I'm a lazy guy. I did that just to put a big one inside. Probably this kind of picture relative simple.
How did you call that? X-ray?
Yeah, because you cut egg tray because you have a lot of common cells like that. You have a lot of small cells.
Okay, so if there are no more questions, let's thank Wei Zhu again.
Okay, thank you.
And there is wine outside maybe already?